any Q&A, so I'd like to thank you again for the very nice talk, and we'll move on to the next speaker. Thank you
for the opportunity.
Thank you. All right. All right. So the next speaker is actually a recorded presentation. This is going to be from Dan Harrison. Dan is a material scientist who has worked in the digital printing field for 39 years. He has a PhD in polymer science for the University of Connecticut and an MBA from the University of Rochester. Dan spent the first half of his career developing digital photographic printing at Eastman Kodak. He now works at ARMOR-IIMAK, an international digital printing supplies company, as their chief technology officer. His current interests include developing sustainable solutions for label, textile, and conductive digital printing. And let me get the video up and running here.
Hello, my name is Dan Harrison, and I'm the CTO of ARMOR-IIMAK, an international digital printing supplies company with R&D operations here in Amherst, New York, near the UK.
We cannot see the video.
You can't see the video?
We cannot see the video. It's the what document.
Thank you. I think perhaps oh, interesting. Thank you. Sorry about that. Here we go. Now you can see?
No, it works well. Thank you.
Oh, yeah. Thank you very much. Sorry about that.
I'd like to thank Professor Guan for inviting me to present at this Radios Day conference. Today, I'll be speaking on the evolution of RFID tags and how factors such as sustainability are shaping the ways in which tags are made. I'll share a vision with you on how RFID tags can be produced directly on packaging materials, such as paper and plastic films. This vision of distributed RFID production provides a means to significantly improve the sustainability of RFID tags without sacrifice to their performance. In this talk, I'll first review the evolution of RFID tags, then I'll describe the various additive processes which can be utilized to produce tags in a both sustainable and distributed fashion. RFID started as a purely analog technology in World War II for detecting friendly aircraft. The widespread use of RFID had to wait for the development of the radio frequency integrated circuit before it became widely used for automated item identification and tracking. The development of the RFID inlay, which integrated the RFID chip along with the antenna on a thin plastic substrate, really triggered the widespread use of this technology. RFID inlays are easily inserted in or onto packages. There's a shift happening in the production of RFID inlays today. Originally, the antennae were formed on plastic substrates using metal etching processes, which generated hazardous waste. Some of the largest tag producers are switching from these subtractive etching processes to additive foil cutting of antennae. I'll describe what I know about this process later in the talk. The next step in the evolution will be to form antennae directly on the packaging materials, eliminating the substrate, the adhesive, and a good portion of the metal, so that we can create a much more sustainable tag. You can see on the slide a carbon-based antenna printed directly on a corrugated packaging material as an example of this evolutionary step. We'll go into some detail on the various additive processes used for antennae formation during the course of the talk. A future step in the evolution of RFID will be the elimination of the chip altogether, printing a chipless tag directly on packaging materials. We'll briefly discuss chipless resonators like the one on the right-hand side of the slide at the end of the talk. As RFID grows from tagging pallets and cases of items to tagging individual items, the issue of sustainability is gaining importance. At the item level, trends in the sustainability of consumer packaging also apply to RFID tags. RAIN, which is an international consortium of RFID suppliers, has formed a working group to address this issue of sustainability. On the slide I've attached this working group's objectives. Two key areas of focus are first, dry additive antennae production, and second, the integration of tags directly into the packaging. Our work at IIMAK is exactly aligned with these objectives. Let's dig a bit deeper into the factors that are driving sustainability in packaging. These include reducing the carbon footprint of packaging by using sustainable or renewable materials, as well as recycling and elimination of hazardous waste. Plastic inlays and the adhesives used to attach them to packages are not sustainable materials. Such inlays interfere with the recycling and composting of packaging. Use of metal etching to form RFID antennas, which I mentioned earlier, generates hazardous waste that has to be safely disposed of. All of these factors are forcing a shift in how RFID is being integrated into packaging. Retail RFID tag manufacturers have gotten the message and they're adjusting. Printed and cut antennae are replacing etched. Paper inlays are replacing plastic. However, there's still room for further improvement. That's what we'll talk about today, forming antennae directly on the packaging substrate themselves. This will be the next big evolutionary step in RFID. Let's now talk about the various additive methods with which RFID antennae can be produced on paper and sustainable substrates. The methods include foil cutting, inkjet printing, thermal transfer printing, and various hot and cold stamp printing methods. Let's start by reviewing metal cutting of antennae. For metal cutting, there's an abundance of patents which describe the process, some using mechanical means such as rotary die cutting, and others using laser cutting and ablation of the antennae. It's difficult to tell which processes are actually used in practice to cut these foil antennae, but it seems likely that first a rough cut is made mechanically, and then lasers are used to create the fine features. If analog cutting is indeed part of the process, then it's not truly digital. Some patents mention affixing the chip to the foil before cutting to avoid having to align and mount the chip on the finished antenna. However, such operations require the ablation of metal between the chip and the contacts to complete the antenna circuit, and this seems very challenging. Antenna cutting processes are a big advance over metal etching and also enable antennae to be formed on porous substrates such as paper. However, foil cutting may not lend itself to distributed RFID tag production, as it's a complex process which is best maintained in a large centralized facility. Additionally, metal foils are typically thicker than necessary for RFID antennae, as they need to be self-supporting to work in this complex process. This results in a less sustainable solution. We'll discuss that later. Let's move on to some of the digital processes for RFID antenna production. First, let's talk about inkjet. Many companies and universities around the world have been investigating inkjet printing for conductive traces and antennae. On the surface, inkjet would seem to be the most efficient, sustainable solution for additive antenna production directly onto substrates. However, like everything, the devil's always in the details. I'll share an example with you of a study done by Tim Drysdale and his colleagues at Tampere University in Finland. They compared RFID performance with antennae printed with inkjet and thermal transfer printing. They found both methods worked and had equivalent read distance. However, the differences between the two methods were in the complexity and expense of the process. Inkjet printed silver antennae needed to be dried and cured before use. This process fuses the dispersed metal particles into a continuous conductive layer. As we'll learn on the next slides, thermal transfer printing produces antennae that are ready to use and quite a bit less expensive than inkjet printed tags. So thermal transfer is an additive printing method, a digital printing method, and we can use this for printing antennae. Thermal transfer is a very simple, reliable process. The printers have very few moving parts. And I think that you'll recognize a very familiar type of printer, the barcode printer on this slide. Such printers are all you need to print RFID antennae as well. In the process, pressure and heat from the thermal printhead are used to transfer functional layers from a ribbon to a substrate. In the case of barcodes, the functional layer is a pigmented black ink, a thermoplastic ink. In the case of conductive printing, the functional layer is a vacuum deposited metal film with a thermoplastic layer coated onto the top of it. Image-wise heating creates an adhesive bond between the metal layer and the substrate. As the ribbon is peeled away, the metal releases from the ribbon to form the finished antennae on the substrate. Conductive thermal transfer printing is a well-established method for printing electronic devices. Many different types of flexible circuits and sensors have been produced with thermal transfer. In this process, we can either print aluminum or copper. Other more expensive metals can be printed as well, but from a cost standpoint, aluminum and copper make the most sense. Vacuum deposited metal is extremely pure and has volume resistivities very close to the bulk metal, so good performance is achieved. The process is capable of printing very fine features. 100-micron gaps or chip mounting is easily accomplished. Thermal transfer printers are capable of printing RFID antenna on almost any flat substrate. And these printers only cost about $3,000, very inexpensive compared to an inkjet printer capable of printing conductive inks. The ribbons are also very inexpensive, and the supplies costs are less than 1 cent per square inch. The conductive thermal transfer printed antennae are ready to use immediately after printing, as I mentioned. With inkjet, the silver ink and inkjet printers are way more expensive. The quantity of silver required is about 10 times that of the aluminum used in the thermal transfer process. Copper-based inkjet inks are less expensive than silver inks, but these inks must be sintered before use. That is gotten up to very, very high temperatures, and this adds additional capital expense and complexity to the operation. Finally, inkjet inks don't print well on uncoated substrates, and they typically need some sort of an ink receptive layer for the high print quality requirements of an antenna. Conductive inkjet printing directly onto paper packaging substrates is unlikely to be successful. Several years back, we asked our friends at Vizinex RFID to help us benchmark our thermal transfer printing processes against etched metal RFID tags. The read range of the thermally printed metallograph ribbons was 70 to 80% that of the read distance for the etched tags. At the time, conventional wisdom predicted that metallograph printed antennae with a thickness almost 2 orders of magnitude thinner than the etched antennae wouldn't have performed so well. We hypothesized that the low resistance and high uniformity of the metal deposition really contributes to this good performance. Later in the talk, we'll discuss how matching the impedance of the thermally printed antennae and the chips, the RFID chips, has really eliminated the read distance gap, providing equivalent tag performance to the etched metal antennae. Let's first focus on the sustainability advantages of thermal transfer printing. The environmental impact of RFID tags, as I mentioned earlier, is an important factor as we all work to improve sustainability of the products we produce and the recyclability of the packaging materials they're shipped in. I've done a rough mass balance here to show that conductive thermal transfer printing direct to the substrate actually consumes about 10 times less materials overall than conventional RFID inlays and doesn't generate any hazardous waste. Starting with the metal consumed, there's actually 50 times less aluminum used than in an etched metal or foil inlay. This is a big sustainability advantage. Aluminum is not a sustainable material as it's mined, and vast amounts of electricity are required to convert aluminum oxide to aluminum metal, creating a big carbon footprint for this metal. So 50x reduction in aluminum usage greatly improves the sustainability of the thermally printed tag. Many people point out that the spent ribbon waste has to be considered, and indeed it does. However, the PET film used for the ribbons is 8 times thinner than the PET film used in the inlay. And since the antenna is printed directly on the packaging material, the inlay substrate and the pressure-sensitive adhesive used to attach it to the package are eliminated. All in all, thermal printing is one of the most green processes for RFID antenna formation. Next, let's talk about some of the work going on in Europe to print antennae directly onto paper packaging materials. Work at the Pulp and Paper Research Institute in Slovakia, called VUPC, is using metallograph to print RFID tags right onto paper in an effort to enhance the recyclability of paper packaging materials by eliminating the plastic inlays from the waste stream. In addition to printing directly on paper, VUPC has done some careful work to match chip and antenna impedance and found that the read range of a tag using a metallograph printed antenna was equivalent to that of the inlays using etched metal antennae. In this work, they were using NXP U-code chips. This is an important result as it validates theory and provides a path for equivalent tag performance with thermally printed antennae direct packaging materials. This work has been published in the Journal of Materials and Technology. Digital printing processes have the unique capability of rapid prototyping. Such capabilities are useful for chip and antenna impedance matching, which is an iterative process at this stage. We have started up a research program with Professor Guan and his colleagues here at UB to better understand antenna design rules for RFID chip impedance matching and to further drive higher tag performance. Early results here at UB are in agreement with the impedance matching work done at VUPC, so that's very exciting for us all. VUPC is taking direct tag production on packaging materials a step further. They're developing these digitally optimized designs, and then they're printing the same design with the same ribbon using more productive analog stamping technologies. So let's talk a bit about productive stamping and how we can take advantage of good impedance matching using the same kind of materials, but very productive, mass productive, capable fabrication technologies for producing tags directly onto paper and film packaging. These are called hot and cold stamping processes, and they provide high volume production capability for tags. VUPC is installing a hot stamping line to transfer antennae from the thermal transfer ribbon to paper-based materials. Both hot and cold stamping processes mirror digital thermal transfer printing, with the exception that they're repetitively printing the same antenna design over and over for a highly productive, inexpensive process. There's several well-established methods for metallic foil transfer. We have seen successful demonstrations with two of these methods using metallograph. The first involves printing an adhesive in a pattern of an antenna or other electronic circuit onto a substrate, and then using that adhesive to adhere to and transfer off the metal layer from the ribbon to itself in an image-wise fashion. Adhesives for RFID antenna production have been successfully printed using flexo technologies, like the example shown on the slide below. However, other methods, such as inkjet printing, may also be successfully used to add a digital capability to printing the adhesive. Metal transfer from ribbon to substrate is typically facilitated with a heated nip roll, as you can see in this slide. That activates the adhesive, causing the metal to stick to the substrate and come off in a image-wise fashion. However, it may also be possible to develop cold transfer processes with pressure-sensitive adhesives. The hot stamping process is a little bit different. In this process, the ribbon or the receiving substrate is coated with a thermoplastic adhesive, which is melted in an image-wise fashion by a cylindrical hot stamp die. So the elevated portions of the die, when they press the ribbon onto the substrate, cause the adhesion to develop between the substrate and the metal, and then the ribbon is peeled off, leaving an antenna on the substrate. These analog printing technologies enable the production of high volume RFID tags at a very low cost right onto packaging substrates. Additionally, these kind of processes are very compatible with the type of lines that are used for printing packaging materials. So these processes can be a drop-in into existing packaging operations. Before we wrap up, let's take a moment to discuss chipless RFID, which is on the horizon. Early attempts at chipless were done by a company called Inksure, now called SureCode, in the early 2000s. They successfully demonstrated that non-line of sight metallic codes printed with our metallograph ribbon could be read with a technology they called synthetic aperture radar. Although Inksure wasn't successful with their SAR code, work on chipless RFID has continued. Pioneering work at Monash University in Melbourne, Australia has put the technology on a much firmer footing from a theoretical standpoint. The benefits of a non-line of sight identification technology are enormous. However, barcode printing is so inexpensive to deploy that RFID has yet to come close to displacing it. If chipless RFID can be printed with the ease of printing a barcode and inexpensive, robust readers can be developed, I believe this technology will be rapidly accepted. Thermal printing processes are ready today to print chipless directly onto packaging, and this would enable a very low-cost means to create a sustainable tag. So let me wrap up. Conductive thermal transfer printing with metallograph can be used for RFID antenna production directly onto film and paper substrates, creating very sustainable packaging solutions. This eliminates the need for an inlay, reducing waste and expense. Metallograph enables customized antennas to be inexpensively printed and optimized for high performance. Leveraging widely used thermal transfer and stamping print methods, capital costs are very low and well adapted to printing directly to packaging materials. Supply costs are well in line for a less than 1 cent tag. Additionally, conductive thermal transfer printing may be one of the most efficient means of creating chipless RFID tags. I would consider all of you who are thinking about RFID technology and incorporating it into packaging materials to consider metallograph thermal transfer printing as a very capable technology to efficiently accomplish this goal. Thanks very much.